Hi everyone. This video is a continuation of the video on row operations on matrices. We saw that row operations allow us to tackle linear systems and their problems with linear algebraic language. However, to know when to stop performing row operations, to know when we got to a solution of our linear system, we introduce the notion of a reduced echelon form for a matrix. Let me describe this form here, and then we'll do an example and see how this form can be used to solve linear systems using matrices. We say that the matrix is in reduced echelon form if the following things are satisfied. First of all, if there's a row of zeros, then it has to be at the bottom of the matrix. Whenever there's a row that doesn't only have zeros, it will have a first non-zero entry, which is called a leading entry. Our requirement is that leading entries in a reduced row echelon form matrix always lie to the right of the leading entry of the preceding rows. Take a look at this example. The leading entry in this matrix here, in the first row of this matrix here, is A. The leading entry in the second row is D, which is to the right of A. And the leading entry in the third row is F, which is to the right of D. So this matrix here satisfies 2. Condition 2 is okay here. Take a look at this other matrix. Here we have a leading entry A and a leading entry D. That's fine. D is on the right of A. However, the leading entry F is to the left of D. The leading entry of the third row is to the left of the second. So 2 is not satisfied here. So this first matrix is potentially in reduced row echelon form if it satisfies all the other points. This one for sure is not, because it doesn't satisfy the requirement that its leading entries are all to the right of the preceding ones. Other requirements for a matrix to be in reduced row echelon form is that all of the leading entries are equal to 1, and all of the leading entries are the only non-zero entry on their corresponding columns. These 4 conditions may sound a little bit complicated like this, but let's see them in an example. Here's a linear system. We can write it as a system of equations here, but as we saw last time, we can write an associated augmented matrix. You see that the columns of this matrix are obtained by looking at the coefficients of the variables in this linear system. So for example, the coefficients of the variable x1 are 1, 0, 1, 0, which are exactly the entries of this column over here. Likewise, all other columns are coefficients of our variables. We'll solve this linear system without looking at equations. We'll only use the augmented matrix. So how do we use the augmented matrix and help ourselves with the reduced row echelon form? Well, let's take a look at this augmented matrix. The first row has a leading entry here. Since this has to be a leading entry, all of the subsequent leading entries need to be at least in the second column or to the right of that. Therefore, we need to eliminate this entry in the third row down here. We can do that by replacing the third row with an elementary row operation by itself minus a copy of the first row. Subtracting the 1 that is in the first row to the third will effectively get rid of that 0. Let's do that. I'm not going to change anything else in my matrix. Minus 1, 1, 0, 2, 1, 1, 0. Now, in this third row, I will subtract the first one from it. So I will have 1 minus 1, that's 0. Then I'll have 1 minus 1 again, that's also 0. 1 minus 0, that's 1. 0 minus minus 1, it will become a 1. And then I have 3 minus 1, that's a 2. That's my new row. I'm not going to do anything to the last one, which remains the same. We used an elementary row operation to get rid of a potentially problematic entry to make our matrix look more like it's in reduced echelon form. Let's keep our game going. Now let's look at leading entries here. We have the leading entry in the first column and the first row. The second row has a leading entry in the second column. That is not a problem. The third row has a leading entry in the third column. So far, so good. There's a problem here. We cannot have a leading entry on the third column in the fourth row. So the way we can solve that is by replacing our fourth row with itself minus the third. We'll subtract the third row from the fourth, and in doing so, this is what happens. Minus 1, 1. The first two rows are unaffected, so I will just copy them. The third row also is not affected by this process. And now I subtract the third row from the fourth, but they coincide. So when I subtract it, I get a row of zeros. Rows of zeros need to be at the bottom for a reduced echelon form matrix, which is fine. That's where this row of zeros is. The leading entries in this matrix are satisfied. They are as they should be in a reduced row echelon form matrix because they lie to the right of the ones above them. However, there's still some other problems. For example, we would have to, well, the leading entry 2 here is not a 1. Therefore, this doesn't satisfy the condition of a row reduced echelon form. What we could do to take care of that problem, and I will do it here, is to replace this row by itself divided by 2. I'm not going to write a new matrix for this. I will just write over this one. If I divide the second row by 2, I get 0, 1, 1/2, 1/2, 0. Now the leading entries are all 1. So the next problem that we need to take care of is the fact that they need to be the only non-zero entries in their columns. And as you see, the first leading entry 1 is indeed the only non-zero entry in its column, but the first and third leading entries have some non-zero elements in their columns, which we need to take care of. Let's get rid of those. To eliminate the 1 in the first row, I will just subtract the second row from the first one. So I will replace the first row with itself minus the second row. In doing so, I get the following. I get a 1 here, 1 minus 1, that's 0. I subtract 1/2, so I get minus 1/2. Minus 1 minus 1/2 is minus 3/2. And then I have 1 minus 0, which remains a 1. Now let's take care of the 1/2 here. To take care of that 1/2, I will take my second row and I will subtract the third row divided by 2. It's 3. So this will take the place of my second row. Let's compute it. We get 0 and 1 because there's zeros in the third row. I have 1/2 minus 1/2 divided by 2. That will give me a 0. 1/2 minus 1/2 divided by 2 is also a 0. And then I have 0 minus 2 divided by 2. That's a negative 1. The last two rows are unaffected by this process. 0, 0, 1, 1, 2. And the last row is a row of zeros. We are almost there. There is one problem left, which is this entry, -1/2. It lies above one leading entry, the leading entry of the third row. So we should use the third row to eliminate it. To do so, we will replace our first row, R1, with the third entry divided by 2. I divide it by 2 so that then this 1 will become a 1/2, and when I add it to the -1/2 I have here, I will get a 0. Doing this operation, so we'll replace R1 with this, we get 1, 0. Then I will have -1/2 plus 1/2 times 1, that will become a 0. The next is -3/2 plus 1/2, that's a -1. And then we have 1 plus 2 divided by 2. So it's 1 plus 1, which becomes a 2. The second row is unaffected by this procedure, 0, 1, 0, 0, -1. And the third row is likewise unchanged. 0, 0, 0, 0. Now, let's go back and check whether we got to a matrix which has a reduced row echelon form. Our matrix has a row of zeros and it's at the bottom. We took care of the fact that leading entries always must move to the right of the preceding ones. The leading entries have been rescaled and multiplied by a constant so that they're all equal to 1. And the leading entries are the only entries in their column. If you look at this matrix, you'll see that all of those 4 requirements are satisfied. So this matrix here is in reduced row echelon form. And sometimes I will write reduced row echelon form for brevity. Once we reduce our augmented matrix to a reduced row echelon form, we can finally interpret the result of our linear system. Let's have a look at it here. Our reduced row echelon form matrix is written here, and now we can translate it back into equations. So every row will become an equation. This first one reads x1 minus x4 is equal to 2. The second one, there's a 0 missing here, reads x2 is equal to -1. The third is x3 plus x4 is equal to 2. And the last one is 0 equals 0. Having one row of zeros corresponds to the fact that one of the variables will be free. And in fact, in this case, the variable corresponding to the fourth row is x4, and that's going to be a free variable. Let's write down these equations as a solution set for our system. It will have a free variable, therefore the solution set will look like this. By just manipulating these equations, I can write that x1 is equal to 2 plus x4. That's what I wrote up here. x2 is equal to -1. x3 is equal to 2 minus x4. And x4 is just equal to itself because it's a free variable. I can rewrite this as the sum of 2 different vectors. There's a vector containing only constants, 2, -1, 2, 0, plus another vector that multiplies the free variable x4. That vector has coefficients 1, 0, -1, and 1. You saw that we solved a linear system using only the augmented matrix and raw operations on it. The way we did it was to reduce the augmented matrix to the reduced row echelon form of it, and then interpreting the meaning of that matrix. What are possible cases, possible outcomes of this procedure? What we did in this example was what I call scenario 1. There's a row of zeros. Whenever there's a row of 0 in the row reduced echelon form, this means that there's a free variable in the system, and having free variables is the same thing as having infinitely many solutions. Other possibilities is that there is a row of zeros, except one of the entries is non-zero, the last one. If that's the case, if you have a row that is all zeros, but the last one is not 0, well, try to translate it into an equation. This equation here is 0x1 plus 0x2 plus 0x3 plus 0x4 equals 1. But that equation is 0 equals 1. It's false. Therefore, the system can never have a solution. This is the signature of an inconsistent system, a system with no solutions. Another possibility is that none of the two previous scenarios happen. So there's no row of zeros, and there's no row in which they're all 0 but the last one. If this happens, and the only way that it can happen is that there's as many rows as there are columns, think about it. By how the matrix is sized, the only way that you have no free variables and solutions is that you have n variables and n equations. In this case, then you have a unique solution to your linear system. I'll see you in the next video.